Exercise 1619 gives you some molecules, and it's asking you to draw the expected H1-NMR or proton NMR spectrum for these. And to draw that, we just want to know about those four different features of the spectrum. We want to know how many signals there are, where those signals are, the location, how much area is going to be underneath the signals, and last but not least, the splitting patterns. So let's dive in on that. First step, draw all of the hydrogens. Now, there really isn't symmetry in this molecule, and the implication is that each of these groups of hydrogens are going to be in their own unique electronic environment. So those yellow ones there are alpha to a carbonyl, and they're further away from the ester side. So they're in a separate environment from these next hydrogens, which are beta to the carbonyl, and far away from the ester side. So that's a different electronic environment. And then these hydrogens here are further still from the carbonyl and even closer to the ester side, so that's yet a new electronic environment. And finally, these hydrogens here are right next to the ester and really far from the carbonyl side there. So we've got four different electronic environments, and so we know that the NMR spectrum should have four peaks. All right, so first feature, where will these peaks show up? What's the location? So we have the number of peaks. Where will each of the peaks show up? First, let's get a general sense of where the peaks will be, and then we'll adjust those numbers based on the electronegative stuff nearby. So we have these yellow hydrogens. Those hydrogens that's a CH2. Normally you'd expect to see a CH2. We'll just watch out unless it's a allylic, which this one's not. It's not one atom away from an atom, a double bond between carbons. So here, this CH2, that is normally going to show up at around 1.2. So we'd expect, in a general way, the peak to show up there. For the brown hydrogens, that's another CH2, so we'd expect, again, those to show up at around 1.2. For the blue hydrogens, that's yet another CH2, so 1.2. And then for the purple hydrogens, that's another CH2, and so 1.2. Once you have a general idea of where these things are going to be, where the peaks are going to be, you have to adjust that based on the electronegative stuff nearby. So for example, the yellow hydrogens are alpha to the carbonyl. So this is the carbonyl carbon. Right next door to it, that's the alpha position. If you are alpha to a carbonyl, then, as you can see down here, you have to add 1 to the parts per million, to the delta value that you'd get for this. So plus 1, and that gives you a total of 2.2. That's where we'll be looking for this CH2 peak. Next, the brown ones. Those are beta to the carbonyl. So again, you have that carbonyl there. We saw where alpha was, and 1 further away, that's beta. If you are beta to a carbonyl, as you can see here, you add 0.2. That adds that to the shift. And so total, you'd expect to find that peak at around 1.4. For the blue hydrogens, those are now too far from the carbonyl to feel the effect of its electronegativity. They would be called gamma. They're not 1 away, they're not 2 carbons away, they're 3 carbons away, that's gamma. And when you're gamma, you're too far away to feel the effect of electronegativity. So that stops feeling the carbonyl, but it does feel the ester side. Right, this is an ester right here. We've been looking at the carbonyl side of the ester. The ester side, though, that's on the right. And here's the alpha position from the ester. The blue hydrogens are on the beta position from the ester. Now, if you're beta from an ester, then notice down here, beta from an ester, you would add 0.6. So you add 0.6, and the total, the place where you'd expect that peak would be at 1.8. So the blue hydrogens, we would look for that peak at 1.8. Next, the purple hydrogens. So those are alpha to the ester. Right, here's our ester side. And those are one atom away, so alpha. Alpha to an ester. If you are alpha to an ester, you can see that that would mean you would add 3 to the chemical shift. Oops. So 3. So that gives you a total of 4.2. So we'd expect to see that peak at around 4.2. All right, we have our different numbers of signals. We have the location for each. I'm going to erase these numbers so this doesn't look too confusing, all of this stuff here. Okay, so we've taken care of the location. The next step is to look at the second feature, and that is the area under the peak. That's represented by the number of hydrogens. And so we would just want to make a note that this will have a height that corresponds to 2 hydrogens, the yellow. The brown will also have a height that corresponds to 2 hydrogens. The blue will have a height that corresponds to 2 hydrogens. And the purple will have a height that corresponds to 2 hydrogens. Straightforward enough. Next, the third feature is the shape. What is the splitting pattern? Now for this, you want to look at how many carbons are nearby, how many hydrogens are on the adjacent atoms. So for the yellow ones, this is where the hydrogens are attached. Let's look at the atom to the right. How many hydrogens are there? 0. Look at the atom to the left. How many hydrogens are attached to that? 2. And so we're going to use that n+1 rule. It's 2, the number of hydrogens adjacent, plus 1, that gives us a triplet. So this is going to, this yellow signal, the signal from the hydrogens highlighted in yellow, that will split into a triplet. And so it's going to look like this, with the 3 spikes. All right, next, the brown ones. So the atoms with the brown hydrogens on them, the atom with the brown hydrogens on them, that's that one right there. And then we'll look next door. Now on one side you have 2 hydrogens in one electronic environment. On the other side you have another 2 hydrogens in a different electronic environment. That's the reason why 2 of the hydrogens are yellow and the other 2 are blue, because they're in different electronic environments. Now the yellow hydrogens, those will want to split this signal in one way. It'll want to split that brown signal into a triplet. The blue hydrogens will also want to split that brown signal into a triplet. So we'd have a triplet from the yellow. The blue hydrogens would also want to split it into a triplet, but with a different amount of energy, because both of these are in different electronic environments. They're going to contribute a different net magnetic field to these hydrogens. And so you would also get a triplet, but it wouldn't line up. And when you add those 2 together, you would end up with basically a mess. Now there is a way to read that, but we won't be concerned with that. We would call that a multiplet. So if you ever have hydrogens on the 2 sides, adjacent hydrogens that are in different electronic environments, so yellow and blue, adjacent hydrogens in different electronic environments, then the signal for the hydrogens in between those will be a multiplet. And so that's what those brown ones will be. Those will show up as a multiplet. And if you want to be, I would encourage you, if you ever have to draw a multiplet, you can draw a squiggle, that's fine. Just write the word multiplet next to it so that it's clear. That's what you mean. Okay. For the blue hydrogens, so here we're looking at, this is the atom they're attached to. It's the atom they're attached to, and then we'd look at the atoms next door. Now, to the left, we have a carbon with 2 hydrogens attached. To the right, we have a carbon with another 2 hydrogens attached. But notice that this is in one electronic environment, that's in a different electronic environment. When hydrogens in different electronic environments surround hydrogens, the signal for the hydrogens between them becomes a multiplet. It gets messy. And so you would show that would show up as a bunch of squiggles that are difficult to read. And so just to clarify that that's what you mean, if you draw that in, write in multiplet next to it. Okay. Last but not least, the purple hydrogens. Those have no hydrogens adjacent above it and 2 hydrogens adjacent below it. So here you have 2 hydrogens on that side. And so following the n+1 rule, you'd have 2, those are the adjacent hydrogens, plus 1, the peak will show up as a triplet. You'll have 3 spikes. So 1, 2, 3. So that gives us all the information we would need to know about each of these peaks in order to draw the NMR spectrum. So let's put all that together and draw the spectrum. We have the y-axis that tells you about the absorption, the x-axis that tells you about the shift in parts per million, how much energy it takes, it increases as you go to the left, to flip the nuclei, compared to the energy it takes to flip the hydrogen nuclei in TMS, tetramethylsilane. So TMS is assigned 0. Now here, our largest number is 4.2, so I'm just going to put this as 5. So we have 0, 1, 2, 3, 4, and 5. Those are our shifts. So first the yellow hydrogens. That signal is going to be at 2.2, and it's going to be a triplet. The height will be for 2 hydrogens. Now the height just is a relative amount, so the height for this is going to have to be the same height as for all of the other peaks, or the area underneath it. So a triplet at 2.2 would be something like that. Next, the brown hydrogens. We're going to have a multiplet at around 1.4, and this should have the same area underneath it as the other signal. Now, if you want to be extra clear, which is always a good idea, write the number of hydrogens next to the peak that you mean. So for the brown hydrogens, we're going to have a multiplet at 1.4. So that would be something like this. And just to be extra clear, I would write 2 hydrogens and a multiplet. For the blue hydrogens, we will have a multiplet at 1.8, and it will be 2 hydrogens in it. So write that. You'd write 2 hydrogens and a multiplet. All right, last, the purple hydrogens. There we're going to have a triplet at 4.2, and the height should be around, or the area underneath should be around the same. So we'd have a triplet at 4.2. The area should be around the same. If you want to be extra clear, you'd write 2 hydrogens. Last but not least, you just connect the signals. We don't have any signals anywhere else, so it's just a flat line, so no shadows being cast. And that would be the NMR spectrum. This beautiful thing right there. Okay, so we'll use these tables again in this next one. You would want to commit these tables to memory. Okay. All right, same deal here. We want to draw the NMR spectrum. First, notice that there is a line of symmetry here. There's a plane of symmetry down the middle of the molecule. Okay, so let's just focus on one side. The other side is just going to duplicate this. So any peaks that we have here, the other side will match it. So if we focus on one side, we'll find all of the peaks that will be in the spectrum, we would just need to adjust for the total number of hydrogens there. Just to illustrate the point in this video, I'll draw the hydrogens in on both sides. But we really only need to analyze one side, the other side will just duplicate it. So these are all of our hydrogens. So first, let's just figure out how many signals we have. We have this aldehyde hydrogen. It's attached to a carbonyl carbon, this carbon right there. And so that is a unique environment. It'll be represented by one signal. Notice this is surrounded by the same exact environment, electronic environment. So both of those hydrogens will show up in one signal. The next signal will be for these hydrogens down here. Now certainly those three hydrogens on that methyl group are in the same electronic environment. What may not be as immediate to see is that the other three hydrogens are also in that same environment, because all of those brown hydrogens are the same distance away from any feature of the molecule. For example, they're both 1, 2, 3 atoms away from the carbonyl. 1, 2, 3. They're also both 1, 2, 3, 4, 5 atoms away from the ether oxygen. 1, 2, 3, 4, 5. Well, if you have the same groups, the same distance away, that's the same electronic environment. And so all those brown hydrogens are in the same electronic environment. So that's the second signal. And the fact that there are so many hydrogens there just means that signal is going to have a larger area underneath it. Next, we have these two hydrogens here. They're a unique distance away from the aldehyde and also from the ether. So that's a unique environment. And then we've got these next two hydrogens. Oh, and while I'm at this, let me just point out the symmetry. Notice these hydrogens here, those brown hydrogens on the other side, those are in the same environment as the thing on the opposite side of the line of symmetry. Likewise, these hydrogens up here are in the same environment as the blue ones. These are in the same environment as those purple ones. The purple ones are both, they have an ether right to the next of them, to one side of them, and they have the same branches, the same aldehyde on the other side of them. All right, then these last hydrogens, those are all one away from the carbonyl in the middle, and they have the same stuff on either side. It's a new electronic environment. So here, notice how many different colors we have. That's how many different signals we're going to have. We have 1, 2, 3, 4, and 5. So this is going to have 5 peaks. Now let's go through all 5 of those and figure out where we expect to have those peaks. So you're going to use these values from these tables. First, we're going to get a general sense, use the information on the table on the left to get a general sense of where the peak would be. Then we'll use the information on the table on the right to see how those peaks will shift based on electronegative atoms that are nearby in the molecule. So the yellow hydrogen is an aldehyde hydrogen. That has a very unique shift. That appears at around 10. Very few hydrogens appear that far down in an NMR spectrum, so that would appear at around 10. Then, the brown hydrogens. Those are beta to a carbonyl. The aldehyde carbon, that's a carbon and a carbonyl. The position right next to it is the alpha position, and both of these carbons that the brown hydrogens are on, those are at the beta position. If you're beta to a carbonyl, then you add then you would add 0.2. Forgive me, I skipped a step. I'm sorry. We're going over these chemical shifts here. We'll adjust them in a second. Okay, so here we have CH3s. CH3s are expected to appear at around 0.9. So these would appear, you think, at around 0.9. For the next ones, these blue ones, that's a CH2. And in general, you'd expect a CH2 to appear at 1.2. Just always watch out, make sure it's not allylic. If the hydrogens are ever one atom away from an atom in a carbon-to-carbon double bond, then the shift will change, and it'll be 2 instead. The purple hydrogens, that's another CH2, so you'd expect those to appear at around 1.2. And the green ones, it's another CH2, so you'd expect that to appear at around 1.2 on average. Okay, so much for this table on the left. Now let's see how those peaks shift based on electronegative stuff nearby. The shift that's due to how close the yellow hydrogen is to the aldehyde, that's taken into account based on the number we got from the other table. That standard number takes that whole feature into account. So notice this hydrogen is not alpha to a carbonyl. It's attached to the carbonyl. And so we don't have add any shift to that. The shift that is coming from the carbonyl was already factored in on that other table. For the brown hydrogens, and this is what we were mentioning a second ago, you have the carbonyl here. The position right next to it is alpha. Both of these other carbons, the ones that the brown hydrogens are attached to, those are beta to the carbonyl. If you're beta to a carbonyl, then you add 0.2 to the shift. And so we would expect 1.1 to be the place where that peak shows up. Okay, next. For the blue hydrogens, we had 1.2. We had 1.2, and you'll notice that the blue hydrogens are also beta to the carbonyl. The carbonyl is right here. The atom right next to it is alpha. The blue hydrogens are the next one over. That's beta. If you're beta to a carbonyl, then you add 0.2. So 0.2, and you get 1.4. That's where we'd expect to find the peak for those blue hydrogens. All right, the purple ones. The purple hydrogens are too far from the carbonyl to feel it anymore. Oh, and actually, let's revisit these blue hydrogens. I apologize. We said the CH2, you would normally expect to see that at around 1.2. We said because it is beta to the carbonyl, you add 0.2. But notice on the other side, it's also beta to this ether. The position right next to the ether is alpha. These are beta to that ether. If you're beta to an ether, then you add 0.5. So we have the original place where you would expect to find a CH2. We have the shift that's due to the closeness to the carbonyl, and we have the shift that's due to the closeness to the ether. You add those three together, and you get the expected shift for those blue hydrogens. So that would be 1.9. That's where we would expect to find that. All right, now the purple hydrogens. Those hydrogens are alpha to the ether. If you're alpha to an ether, then you add 2.5. So we'd add 2.5 to this because of the closeness to that ether oxygen. And so that's on one side. On the other side of the purple hydrogens, the other side of that, we're too far from the carbonyl. The carbonyl's here, the alpha position is here, the beta position's here. The purple hydrogens aren't alpha or beta, they're gamma. And by that point, you're so far from the electronegative group that you don't feel the effects of the electronegativity anymore. So you'd only add numbers if you're alpha or beta to an electronegative atom. So here we only have the number coming from the proximity to the ether, and so it's 1.2 plus 2.5. That's 3.7. So that's the shift you'd expect. That's the place where you'd expect to find the peak for the purple hydrogens. Now for the green. The green hydrogens, on one side, they're alpha to the ether. So there's the ether oxygen, right next door, the alpha position, that's where you have these green hydrogens. If you're alpha to an ether, as we just saw, you add 2.5. So that's because of the effect of the ether oxygen. Notice, though, that these hydrogens are also alpha to a carbonyl on the other side. You have the carbonyl carbon right next door to it. That's the alpha position. That's where you have these hydrogens. They're alpha to a carbonyl. And if you're alpha to a carbonyl, then you would add the 1. So if you add all of that together, that's where you'd expect to get the shift for that. And so you would have 4.7 as the place where that peak should show up. All right, let me erase this arithmetic so that we have room to find the other features of the molecule. So we'll clean this up. These are the places where we're going to draw these peaks when we draw the NMR spectrum. Okay. So we have in green, this was 4.7. All right, so that's the location of the peaks. So we have the location. Second, we want the area underneath each of the peaks, and that just has to do with the number of hydrogens. So here we have 1 hydrogen. Here we have, in the brown, we have 6 hydrogens, so that's going to be a much larger peak. It's going to be more area underneath that. In the blue, we have 2 hydrogens. The purple, we would have 2 hydrogens, and the green, also 2 hydrogens. All right, so that's the second feature, the area. Third feature is the shape. These are the splitting patterns, and for that, we're going to use the n+1 rule. If we look at the yellow hydrogen, look at the atom next door, the atom next door to where the carbon that the yellow hydrogen is attached to. That carbon does not have any hydrogens on it. In other words, there are 0. So the splitting pattern will be the number of adjacent hydrogens plus 1. It'll be a singlet. So that yellow hydrogen will show up as a singlet. For the brown hydrogens, the carbon next door to the carbon attached to them, that has 0 hydrogens on it. So the splitting pattern will be the number of adjacent hydrogens, 0, plus 1. So that will also show up as a singlet. It'll be a taller singlet because we have 6 hydrogens as opposed to the 1 that we had with the yellow, but it'll be a singlet. The blue hydrogens. On one side, to the left, the carbon that's adjacent to where those are attached has 0 hydrogens. On the other side, the carbon adjacent has 2 hydrogens. So that's 2 hydrogens, 2 adjacent hydrogens, plus 1, because it's the n+1 rule. So that's going to split into a triplet. 1, 2, 3. The purple. To the left, the carbon has 2 hydrogens on it. To the right, the atom doesn't have any hydrogens. So we have a total of 2 adjacent hydrogens. The rule is n+1. So we take those 2 adjacent hydrogens, add 1, and the splitting pattern will have 3 spikes. It'll be a triplet. Finally, the green hydrogens. Those to the left have 0 hydrogens on it. To the left there are 0 hydrogens on that atom. To the right there are 0 hydrogens on that atom. So there are 0 adjacent hydrogens. The splitting pattern will be the number of adjacent hydrogens, so 0 plus 1. So we'll just have 1 spike in that peak. So it'll be a singlet. Okay, we have all of our pieces. we have all of our pieces, and we're ready to put them together to draw the spectrum. So let me clean this up just a small bit. All right. So we're ready to draw our spectrum. So we have, and actually, let's get some space up here. So we have our y-axis where the shadows are going to be cast, and we have our x-axis, y-axis where the shadows will be cast, and our x-axis where we'll see the chemical shift. How much more energy did it take to flip these protons than it took to flip the hydrogens in TMS? That's assigned a value of 0. That's what we'll compare our energy values to. And those are called delta values. They're shifts, and the units are in parts per million. First, okay, so our biggest number here looks like it's going to be 10, so we want to make sure that's included in the graph. So we'll have 10 right here, and we can fill in the numbers as we go. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, first the yellow. Yellow is going to be very small. It's only representing one hydrogen. It's going to be a singlet at 10. So at 10 we'll have a singlet, and it's pretty small. And if you want to be extra clear, you can write 1 hydrogen. The brown hydrogens, we're going to have a singlet again. It'll be 6 times as high, and it's going to appear at 1.1. So here, 1.1, we have a singlet that's 6 times as high. And if you want to be extra clear, 6 hydrogens. The blue, we have a singlet. This was going to be a singlet, right? Because there were 0 adjacent hydrogens, so a singlet. Or I'm sorry, a triplet. If you look at these hydrogens, I'm sorry that they got erased. If you look to the left, there are no hydrogens on the adjacent carbon. If you look to the right, there are these 2 hydrogens. So it follows the n+1 rule. Adjacent hydrogens plus 1, it splits into a triplet. So you get 3 spikes. So we'll have that triplet on these at around 1.9, and it'll represent 2 hydrogens. So 1.9, we have a triplet. It'll be a third the size of this. So 1, 2, 3. That's the blue hydrogens. Next, the purple hydrogens. Here, we're going to have a triplet representing 2 hydrogens at 3.7. So 3.7, a triplet, same size as the blue one. Should have around that same area. And if you want to be extra precise, 2 hydrogens. Okay, that's the purple. Now for the green, we have a singlet representing 2 hydrogens at 4.7. So 4.7, a singlet, about that same amount of area. So that's 2 hydrogens. So those are our peaks. We just want to connect them. So connect that yellow to the green, green to the purple, purple to the blue. And that is our beautiful, very carefully crafted NMR spectrum for this molecule. Now technically the absolute value of the numbers of hydrogens will be twice as large, because remember they're duplicated, but the NMR spectrum doesn't give you the absolute value. It gives you the relative value of the peaks. So these relative values for the peaks are representative of the relative strength of the signals in general, even when you duplicate the two sides. So that would be the NMR spectrum for this. So the general step for drawing the expected H-NMR spectrum, draw the hydrogens. Find out how many are in different environments, then you know your number of peaks. For each peak, find the location, the area, and the shape, and then just draw them on the spectrum.